Welcome back to the IB Math Doctor channel, and today's topic is derivatives and rates of change, or the limit definition of the derivative. If you've not already watched the previous video on limits, that would be definitely a helpful one to watch to help you prepare for this. You can go ahead and click the link on the screen right now, and that'll take you to part 1 of 2 of those videos. And as always, please remember to like, subscribe, and if you want a copy of these guided notes, go ahead and throw your email address in the comments and I'll send them over to you once you've liked and subscribed. So today we're going to do something which is not actually in the standard level analysis and approaches IB syllabus, but it really helps to get a good understanding of how derivatives work and how limits are connected to derivatives. So we're going to explore this thing called the tangent problem. So we're going to think about a function that we've got drawn right here, and we're going to think about a tangent line and finding the slope of that tangent line. So we've got a random function drawn here. It could be some kind of cubic, but we're not really interested in the function that made that shape. And we have a point of interest, which we'll call A, and it has an output value, which we'll call f of A. So the first thing we're going to do is sketch what we think the tangent line might look like there. So we know from the previous lesson that a tangent line is a line that just touches the curve at this point of interest called x equals A. So we'll draw something kind of like that with that red line. This red line will be our tangent line. So our whole goal in this class is to find the slope of that red line that just touches the curve at that point x equals A. And in the previous class with limits, we've built all the tools we need to actually find what the slope of that red line is. So we begin by thinking about another point on the x-axis, slightly further away from this point A. So we'll go some distance away from A, and we'll call that distance h. So our second point will be A plus h, and for illustrative purposes, I've drawn it quite far away. And we know that point also has a y value, which would be f of A plus h. We can do a secant line between these 2 points, so we can take these 2 points and connect them with a chord. And then we can use our gradient formula to find the slope of that secant line, that green line right here. This green line, this is what we're calling the secant line. Okay? So if we go ahead and write an equation for the slope of that secant line, slope of secant, we know that that's calculated just using the gradient formula. So y2 minus y1 over x2 minus x1. We're going to write it in terms of functions here. So in this case, it would be the difference in the y values. So f of A plus h minus f of A. That is the change in y. That is the top y value minus the bottom y value. Okay? And then in the denominator, we would have the change in x. So the change in x will be the difference in our two x values. So that is A plus h minus A coming from those values on our x-axis down there. Okay. We can simplify this down a little bit. Okay. Nothing really changes in the numerator. It's still f of A plus h minus f of A, and then this is divided by A plus h minus A. It's pretty clear to see these two a's cancel, so we're just left with h in our denominator. Okay. Now you're probably thinking that secant line doesn't look anything like the red tangent line, and I would agree. So how do we make this line closer to the tangent line? How do we make the slope closer to that of the slope of the tangent line? Well, we want to move this point A plus h. We want to move this guy closer to A. We want to slide these 2 points together, thinking about A as fixed, and moving that A plus h back in towards A. Can we move them to be right on top of each other? No, because that would make this h value 0 and would lead to division by 0 in our secant line equation. So how close can we move it? Well, we can move it infinitely close together using the tool that we learned in the previous class, which is a limit. Okay? So we're going to use a limit on this definition, and we're going to look at the limit as h approaches 0. So what's happening there, we're taking these 2 points. One of them is fixed, the one on the right side is fixed, and we're sliding the one on the, other way around, we're sliding the one on the right back towards the one on the left so that they are infinitely close together. Okay? When we do this, we arrive at the limit definition of the derivative, which is known as the slope of the tangent line. Okay? So through this little exercise here looking at tangent lines, we have derived the limit definition or the slope of the curve at any point. Okay? The IB denotes this using an F prime notation. So this F with this little apostrophe right here, they denote this as F prime, or they use this other notation, which is called dy dx. Okay? It is given in the formula booklet for higher level students, but again, standard level, it is not going to be tested, but it is a good thing to know just to help you get a better understanding of differential calculus. And we change from it being a tangent line at a particular point to a tangent line at any point. So they will change, we will change the A to be more general and just make it an X. Okay? This way we get a function which can tell us the slope of the tangent line rather than having to compute the slope of the tangent line at every single point. Okay? Now you might ask, why are the different notations here? And this is where we can get into a little bit of math history. Okay? There's actually a lot more notations than what we have listed here. So we have listed dy dx and f prime of x. Okay? Some people like to combine the prime notation and the d notation, and they make y prime. Some people even combine and do df dx. Okay? There is another notation which is called an operator, where you do d dx, that's telling you derivative with respect to x, and then whatever you put in these brackets, that's what you're trying to take the derivative of. So why are there so many different notations? It actually comes from two of the most famous mathematicians in the world who were both trying to study and derive calculus independently. We've obviously got Newton in the 1600s and a German mathematician, Leibniz, who were both working on calculus independently, and they both had their own notation. I don't quite remember which one is which, but one was the prime notation and one was the dy dx notation. And rather than crediting a single one of them with inventing calculus, we honor them both with both notations. And as an IB student, you should be able to read each notation. So if the IB presents a question with an f prime, you should know what that means. If they ask you to find dy dx, you should know what that means as well. So when we want to indicate that we're going to compute a derivative using this limit definition, the IB would specify on a higher level exam that they want you to find this definition using either the limit definition or what is called first principles. Okay? You are essentially finding that derivative from the basic building blocks that make up the slope of a tangent line. Now in our next video in 5.3, we're going to go through a bunch of shortcuts and allow us to do derivatives with real fast speed. It'll turn some of the derivatives we're going to do on the next page into one-line problems. But in order to appreciate the power of those shortcuts, we need to do some problems using this longer limit definition. So that's what we'll do on the next page. We're going to jump right in. We're given a function here. F of x is 3x squared plus 5x, so that's a parabola. We're asked to find f prime. We know this means the derivative. Okay? The only tool we have to find derivatives right now is the limit definition, so we'll have to use that. Okay? And then we've got a command term here, which is hence. They want the gradient of the tangent line at x equals 2 and x equals 4. Now, to really understand what's going on here, I'm going to recommend we draw a sketch. So we're going to sketch this parabola over on the side, and then we'll get into our algebra-heavy derivative calculation using that limit definition. Okay? So you can definitely review drawing a parabola like this, 3x squared minus 5x. I know straight away that it passes through the origin. 0, 0 would be a solution. It opens up, and if I set it equal to 0, I can find the other root, the other 0, the other x-intercept, whatever you want to call it. Simple piece of factoring allows us to take out one of the x's, and we get x equals 0, and 3x minus 5 equals 0. If we solve this other equation, the other root is at 5 over 3, so a little over 1, but less than 2. And we know it's a parabola that opens up because the leading coefficient is positive. So we can go ahead and throw down a quick sketch of it right here just to help us interpret what we're finding at the end. Okay? So the question asks us to find the derivative function, and then it asks us to find the tangent line or the gradient of the tangent line at two values. So x equals 2. It wants us to find the tangent line or the slope of the tangent line right here. I'll draw that in red. And then again at x equals 4, it wants us to find the slope of the tangent line right there at 4, which we'll draw in purple. Okay? So just from this picture, we can tell that we should get a steeper, more positive slope when we substitute 4 into our derivative. We should get a still positive, but not a steep slope when we substitute 2 into our derivative. So we're going to confirm that at the end of this example once we have that derivative equation calculated. So we'll bring that limit definition over. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This is just copied from the previous page. Okay? Now we have to set this up and evaluate this limit. Okay? So limit as x approaches 0. We're going to take our function highlighted in green. Everywhere we see an x, we're going to replace it with a parenthesis and an x plus h. Okay? So this piece that we've just drawn right here, this section in orange is that part underlined there in orange. We complete the numerator by subtracting the original function. Make sure we put a parenthesis on that so it is all subtracted. If we don't, that negative will not distribute and our derivative will be incorrect and almost impossible to calculate. And finally, we have an over h right here in the denominator. Okay? So if we're lining this up with our definition in red, you should be able to see how the pieces connect. Now, from our previous class, we know our first step when we try and evaluate limits is just to direct substitute in. Okay? Obviously, that's going to fail here, as it will in every time you use this derivative definition, because you've got this h in the denominator, and h is going to 0, so you'll be dividing by 0. So we have to employ one of our algebra techniques in order to simplify this down and get this evaluated. Okay? The technique we need right here, we just need to multiply all this out and hope that some of the stuff cancels. Okay? So we take the first parenthesis and we multiply it out. You can do that on the side if you need to, but x plus h squared, that should turn into x squared plus 2xh plus h squared. We'll have minus 5x minus 5h minus 3x squared plus 5x. That's where that parenthesis and distributing that negative really becomes important. And this is still all over h. Okay? It looks like we're making this a lot more complicated, which we kind of are at this time. But if we have a little faith in distributing, we are about to get a much simpler equation for our derivative, as a bunch of stuff should cancel in this next step. Okay? So we keep applying our algebra, and our 3x squareds cancel, our 5x's cancel, and we have 3 terms that remain. 1, 2, 3. If we look at these 3 terms, we can see all of them have a common factor. That common factor is that h. So we can take out that common factor and use it to cancel the h that's in the denominator. Okay? So if we take this out, what am I missing? Oh, that 3h, that was a 3h squared, my apologies. So we'll have a 3h right there, minus 5, all over our h. Okay. Once we have that common factor, we can cancel that h in the denominator. That h in the denominator was the h that was giving us trouble when we were trying to substitute in our limit. So now that it's gone, let's try and substitute in again. Don't forget, we're substituting in for h, so that h is being turned into a 0. 3 times 0 is 0. So that goes away, and we are left with simply 6x minus 5. Okay. And that's it. We've actually calculated our first ever derivative right there. This is an important moment in our calculus careers. The second part of the question can now be approached, which is to find that gradient of the tangent line at x equals 2 and x equals 4. And all we need to do that is take this f primed equation and substitute in our two x values. Okay? This 6x minus 5 is incredibly powerful for us. It can tell us the slope of the tangent line at any x value by simply substituting in. So the first one I will substitute in 2. So 6 times 2 minus 5. That's 12 minus 5, which I believe should be 7. And then the second one is 6 times 4 minus 5, which if my math is correct, that should be 19. So what does this mean for our picture? This means that our red tangent line up here at the top had a slope of 7, and our purple tangent line had a slope of 19. Both positive slopes, one being steeper than the other, just like we thought would happen. So that's how we calculate a derivative using this limit definition. If that's enough for you, feel free to stop the video there. Don't forget to like and subscribe, and go to our next video, which is going to be on those derivative shortcuts. If you want to follow one more example, we can do that right here for a different function, g of x. Okay. This is a square root function, and we're asked to find the gradient at x equals 25. So very similar, but just one evaluation at the end. I always like to sketch to make sure I'm understanding what's going on, especially when these IB problems get more challenging. So in this case, we're talking about a square root function. That looks like a sideways parabola. It's a terrible drawing by me. I'll redraw that a lot better. Square root function looks just like this. So this would be our g of x, our square root x function. And we are interested in the slope when x equals 25. So quite a long way out here on the right side. Okay? We expect the tangent line to be pretty flat, not quite horizontal, but pretty flat. So we're expecting a tangent line slope or gradient to be a small but positive number. All right, let's get into the algebra as we start looking for that g primed of x equation. So we have limit as h approaches 0. Limit as h approaches 0. G of x plus h this time. G of x plus h minus g of x all over h. And we'll go a little faster on the algebra of this one. Okay. So we set up this composition. We've got to keep the limit there until we can substitute it in. We know we obviously can't substitute it in straight away because we'll be dividing by 0 in that denominator. So this is the square root of x plus h minus the square root of x all over h. The algebra technique we need in order to simplify this down, we actually need a conjugate here. If you're not sure how a conjugate works, feel free to go back and watch the limits part 2 video from 5.1. So we will multiply by this same square root, but with a subtraction in the middle. So square root of x plus h minus the square root of x. That creates a difference of 2 squares for us in the numerator. So when we FOIL this out, first times first, those square roots should cancel. So we'll have x plus h. The outer and the inner should cancel each other out. We'll write them here just to make sure. So outer times outer would be plus the square root of x plus h times the square root of x. Inner times inner, that would be minus the square root of x plus h times the square root of x. And finally, last times last, square root of x times square root of x would just be x. I should have had a positive here, shouldn't I? There we go. Didn't do my conjugate correctly. That will give us a final minus x at the end. The denominator, we could multiply it out, but again, we're trying to cancel that h sitting there right at the front, so let's just leave it as is so that it can cancel in the numerator a lot easier. Our square roots cancel just like we wanted, as well as our x's, leaving us with simply an h in the numerator, beautifully positioned to cancel the one in the denominator for us in the next step with the division. Okay. So we are very close to finding our g prime of x right here. We've done the hard work in the algebra. These h's cancel. Don't forget that leaves you with a 1 in the numerator. There is always that implied 1 left. It does not take you down to 0. The h in the denominator has canceled, meaning we can substitute in 0 for the remaining h. The limit can go away. This should leave us with 1 over the square root of x plus the square root of x, which is 1 over 2 square root x. And that's it. We've done it. That is our second successfully calculated derivative. All that remains is to take this derivative and substitute in our 25 to get the slope of our red tangent line. 1 over 2 times the square root of 25 should be 1 over 2 times 5, which is 1 over 10, a very small positive number that aligns with that flat positive slope we saw in our sketch. Well, that completes our work on the limit definition of the derivative. Thank you for watching, and please stay tuned for our next lesson, which will give us some shortcuts to take derivatives in 1 or 2 lines. So in the next class, we will be able to go from functions such as these polynomials to their derivatives in 1 line or less. So you should definitely stay tuned, because that will be a good thing to see.